this assessment asks us to show the mechanism of the reverse reaction of what is illustrated on screen. I've labeled these as going from A to D. We'll see how those labels matter in just a second. The principle of microscopic reversibility tells us that if the fastest way from A to D is through intermediates B and C, it must also be true that the fastest way from D to A is through those same intermediates. And so really the mechanism that we're going to draw is simply the reverse of each of these steps. So let's start with the alcohol that is represented by D. This will react with HBr in an acid-base reaction to protonate the hydroxyl group. Note that we're starting with D, the alcohol, and HBr, just like it is over here. And we make the protonated alcohol plus Br minus, which is exactly what we had for C. C being the protonated alcohol and Br minus. The next thing that needs to form is the carbocation. We've created a good leaving group. That terminology will make sense later on. But that means that this oxygen is going to take its pair of electrons. Again, the reverse arrow of what we saw in the forward direction. When that happens, we end up with a carbocation plus a water molecule. You'll note that the carbocation plus a water molecule was exactly what we had for intermediate B. So we have reproduced intermediate B in the reverse direction. What's left to happen now is that Br minus is going to attack that carbocation, negatives attacking positives, to give us this alkyl halide. We still have water around, but this alkyl halide, this bromoalkane, is represented by A. So it's the same alkyl halide, the same bromoalkane that we had in the forward direction. So by showing the mechanism in this way, we realize that we've gone once again through C and B to get to A, just like we went through B and C to get to D. And so this is an application of the principle of microscopic reversibility that says the fastest way forward is the fastest way back.